In Chapter 6, we're going to talk about the proton transfer reaction, which will be the first of our main reaction chapters. In this section of Chapter 6, we're going to specifically talk about acid-base chemistry. So to quickly review, one of our definitions of acids and bases is the Bronsted-Lowry definition, where an acid is anything that donates a proton, and remember the proton is the H+ ion, and a base is anything that accepts a proton. So when we look at our acid-base reaction, we have our acid, which we typically denote as HA, so that it has that H+ ion that it can donate. And then we have our base, which we're going to represent as the B, and the only thing that a base needs to contain is that lone pair of electrons to accept the proton. When we look at our full reaction, most of our reactions fall under equilibrium conditions, so we can reverse them. So on the product side, we have another acid and another base, and we label them as the conjugate acid and the conjugate base. So the A- ion that we produced becomes our conjugate base, and the H+ ion, Hb+ ion that we created becomes our conjugate acid. So one of the things that you want to make sure that you remember are those lovely conjugate acid-base pairs, where it's an acid on one side, but it becomes the base on the other side of the equation because of the transfer of the proton. The base is then going to be paired with our conjugate acid on the other side of the equation. Conjugate acid-base pairs differ by the H+ ion. Each one of these proton transfers is going to become a single elementary step in many of the reactions that we're going to be looking at in the future. An elementary step is going to be a distinct step in a mechanism that shows how specifically bonds are broken or bonds are being formed. So many of our mechanisms are going to have multiple different elementary steps associated with them. So to look at the mechanistic step associated with our proton transfer, we start off with our acid HA, and we have our base that has the lone pair of electrons. Those lone pair of electrons are going to go to form a bond between the base and the proton, and the bond between the hydrogen and the A is going to break, and that's going to become the lone pair of electrons on our A species. So our product is then the A- that has the lone pair of electrons, and then we have Hb that now has a positive charge associated with it. So you want to make sure that this becomes oftentimes one of the beginning or one of the ending steps for our multi-step mechanisms. With our acids, we can have strong acids. Strong acids are going to be acids that dissociate or react completely, 100%. And we also have weak acids. And weak acids are going to be the acids that only dissociate or react slightly, so something less than 100%. Most of our organic acids are going to fall in this weak category. We can define the amount of dissociation that an acid demonstrates through the acid dissociation constant, which is represented as a capital K, lowercase a. This is a typical equilibrium constant, just specifically representing the acid dissociation. So it describes for us how much a weak acid will dissociate. So if we look at the weak acid dissociation in water, we have HA and H2O reacting to produce H3O+ and the A- ion. So when we get ready to write our Ka expression, equilibrium expressions are always products over reactants raised to their coefficients. So the Ka expression becomes the hydronium ion concentration times the conjugate base concentration all over the original acid concentration. Remember, we're going to ignore water because it is a pure liquid, and its concentration is basically constant throughout the entire process. So for most of our equilibrium expressions, we will end up ignoring water when we talk about acid-base or aqueous-based reactions. When we get into organic-based reactions, we will often look at water concentrations in our equilibrium expressions because water is typically not soluble with most of our organic compounds. When we talk about the Ka values can range anywhere from 10 to the 15th to 10 to the -60. So we have a very wide range of acid strengths. Anything that has a positive exponent, so things like 10 to the 15th, these are going to be very, very strong acids. When we look at our acids that have values 10 to the minus power, like 10 to the -60, these become very, very weak acids for us. For us in organic chemistry, we are mainly going to be looking at a range of 10 to the -5 to 10 to the -15th is where most of our common organic acids will fall. So you can see they will be weak acids that favor the HA and do not favor the hydronium and conjugate base concentrations. Since so many of the Ka values have that 10 to the power associated with them, oftentimes instead of looking at the Ka value itself, we will be looking at the pKa value. To calculate the pKa value, we just take the negative log of the Ka value. This is our typical peak scale. What this then tells us is it converts all of our Ka values into nice integer values so that we don't have to look at those powers. And what we see for stronger acids is that they're going to have smaller pKa values. If they're truly a strong acid, the pKa value will be negative. Then this implies for us that the larger the Ka value is, the more dissociation that we have, the more it favors the products. If we have weaker acids, we're going to have larger pKa values. So pKa values of 14, of 18, 26, 30. These would then represent those smaller Ka values, the ones that favor the reactant side more than they do the product side. Table 6.1 has some common pKa values for you in your textbook, or you could just look up a table on Google for Ka values, and you will get a wide range of them for most common acids and bases, especially organic acids and bases. You do not need to memorize any of these values, but you do need to know how to utilize them, because these values are going to help us predict the reactivity of our acid-base chemistry. Because what we're going to see in our reactions is that stronger acids have weaker conjugate bases, and weaker acids have stronger conjugate bases. So we see this strong-weak relationship. And because of this relationship, we can help predict what side of a reaction we favor. Do we favor the reactant side as a whole, or do we favor the product side as a whole? And what we're going to see in our reactions is that we're always going to favor the weaker side. We're going to favor the weaker acid and base. So what this means for us is that that H+ ion goes from the strong acid, it reacts more with the strong acid, and it goes to the strong base. So once again, the strong base is more reactive than the weaker base. So we're always going to favor the weaker side. So if we actually look at a reaction and do some comparisons, I'm just going to go back to a very inorganic example where we're going to look at HCN and reacting that with the hydroxide anion. Through this acid-base reaction, we will produce water, and we will also produce the cyanide anion as well. So what we want to do to be able to decide with this weak acid-base chemistry, do we favor the reactant side or do we favor the product side? And in order to do that, we're going to look at pKa values of the acids. So the HCN, if I look it up in a table, has a pKa value of 9.31. The acid on the other side is water. So if I look up the pKa value of water, it is 15.74. So again, I have looked those up in tables. I would not expect you to memorize any pKa values this semester. But now in order to determine which side of this reaction we favor, I have to compare strengths. And I'm always going to favor the weaker side. So we said the lower the pKa value, the stronger the acid. So in this relationship, the HCN is considered stronger and the H2O is considered weaker. Now that I have this relationship, I can now tell you which side we favor, and we always favor the weaker side. So when I actually get ready to draw appropriate equilibrium arrows, I'm going to favor more the products than I do the reactants. So this is how we will use pKa values to help us predict, do we favor products or do we favor the reactants? And in this side, this reaction will proceed towards the product side. I can actually now quantitatively determine the equilibrium constant for this equilibrium reaction as well. So that would be our KEQ expression. And I can do that by taking 10 to the pKa of the product acid minus the pKa of the reactant acid, or 10 to the change in the pKa value. What this means for us, remember, change is always final minus initial, so it's the final, which would be the product, minus the reactant. So in this scenario, it becomes 10 to the 15.74 minus 9.31, which would become 10 to the 6.43, which if we plug that into our calculator gives us a value of 2.7 times 10 to the 6th. So you can see with this relationship, it does favor the product side. We have a value that is greater than 1. so it will favor the product side, which was our original prediction based on those pKa values. With all of this information on predicting reactions, we also need to be able to do a little bit of predicting what species can exist in our solutions. And this is going to go back to the leveling effect. And the leveling effect is going to dictate the maximum strength of an acid or a base that can exist in a solution. And this is going to help us predict when we start talking about reactions, will a reaction happen under certain solvent conditions? So what we're going to see is that the strongest acid we can have is always going to be the protonated solvent. And the strongest base that we can have in a solution is going to be the deprotonated solvent. So once again, we go back and we start comparing pKa values to help us do this prediction of if certain species will be formed under certain solvent conditions. So let's look at an example of producing the H3C minus, the carbon ion, the methane ion in solution. If I want to look at producing this in an aqueous-based solution, I would need to be able to compare the reaction between the anion, that base, and the solvent that we have, which would be water in this scenario. So through this relationship, it's just a proton transfer. So I would have CH4, and I would also be producing OH minus. So this would be the reaction of the anion that I want to produce with the solvent water. So what I need to do once again is I need to compare pKa values to decide if I can actually produce this carbon ion in solution. So the pKa of water, again, is at 15.74. If we look up the pKa of CH4, it is 48. So under this condition, if we compare, water becomes the strongest and my CH4 becomes the weakest acid that we have. Which means if we actually compare this equilibrium, the equilibrium highly favors the product side. So what this means for us is I cannot produce that H3C minus ion under aqueous-base conditions. It will always get protonated by the water because that water is the strongest acid that we would have. It is much stronger than the CH4 being the acid. So we would not be able to produce this ion in a reaction under aqueous-base conditions. So let's look at another example. We'll use the same anion, so H3C minus, but this time instead of using water as the solvent, let's use ethane as the solvent. So CH3CH3, and we're still going to be producing the exact same product, so our acid-base chemistry, so CH4. And then our new anion would be the CH3CH2 minus ion. So again, out of our two acids, we're going to compare them. So ethane's pKa is 50. Methane's pKa is still 48. So now through this comparison, methane becomes the strong acid and ethane becomes my weaker acid. So in this scenario, we can now favor the reactant side over the product side. Not significantly, but remember these are p-scales, so it's a tenfold in Ka values that we'd be looking at. So we do favor the reactant side over the product side, which means in a reaction, I can produce the H3C minus anion if ethane is my solvent instead of water. So this once again comes in handy as we start running reactions and helping us predict what ions, what species we can produce under what solvent conditions. And this is referred to as the leveling effect. So we also want to quickly review Le Chatelier's principle because we are going to be dealing a lot with equilibrium processes. And Le Chatelier's principle tells us that if a reaction is at equilibrium and it experiences a change in reaction conditions, the reaction will shift to reestablish that equilibrium. So this is Le Chatelier's principle for us. So if we put this into the context of our acid-base reaction, it tells us that if we do anything to manipulate this position by adding in acids or by taking away acid by adding in base, we can create either more reactants or more products due to a shift in equilibrium. We always shift to replace anything that we have added. We always shift to consume anything new that we have added as well. So we want to be very, very careful to remember Le Chatelier's principle. One of the things that comes from Le Chatelier's principle is that we can actually calculate the percent dissociation of the acid in equilibrium conditions. It's a typical percentage where we're going to calculate the percentage of the part, so that would be the concentration of the conjugate base under equilibrium conditions, divided by the initial concentration of acid that we put in times 100. And what we're going to see is that we can adjust the percent dissociation by impacting the pH of our solution. If we increase the pH by adding in more H3O plus ion, we will actually decrease the percent dissociation that we have due to the shift in equilibrium that we produce. So one of the ways that we can manipulate is through a pH. Let's quickly review pH. Remember, pH is equal to the negative log of the hydronium ion concentration. Anything that has a pH greater than 7 will be basic. Anything that has a pH equal to 7 will be neutral. And anything that has a pH less than 7 we consider to be acidic. So we talk a lot about acid-base chemistry and defining the types of solutions that we need based on these pH values. One of the other things I want to quickly review is going to be that of buffers. Oftentimes we will generate buffers in our reactions. Remember, a buffer is any solution that resists a large change in pH when an acid or base is added to it. We generate a buffer by making it with the acid and its conjugate base, or by using a base and its conjugate acid. It's that relationship between the conjugate acid-base pairings that allow this solution to resist large changes in pH. Along with this, this is the Henderson-Hasselbalch equation. This is the equation that allows us to calculate the pH of a buffer by accounting for the ratio of the acid and the conjugate that we have. So the pH of our buffered solution would be equal to the pKa of the acid plus the log of the conjugate base over the initial acid that we have. If we have buffers that contain equal amounts of the conjugate and the acid, the pH is nicely equal to the pKa of the acid that we are dealing with. So we can use buffers to help establish more of a consistent pH when we are running reactions, so that the pH is not impacted by any secondary reactions that we are running or by any solutions that we add into our aqueous base conditions, which could impact other reactions with our organic chemistry. So oftentimes we will run our reactions under these buffered conditions.